Okay, where are we? Oh, we're here. Right. So let's see. So as not to waste time, I put up some problems, and this is kind of a selection of problems from the sections that I put on the kind of the preparatory sheet. And I think what I'm going to do is I'll show you how to do it. I may not work it all the way out because we already did an example of row reduction. And so I'm going to assume that you know that you've mastered that. That is, you will never be required to reduce more than 3 by 3, and even the 3 by 3s will be relatively easy. That's a mechanical skill. In practice, people never do it. They'll just do it with software. But you do need to understand the principles involved. Right? All right, now, so let's go ahead and do this problem. 1.7 says intersect these planes. Now, these are planes. I do want to give you some idea of the geometrical intuition here. These are planes. This is 111 times t plus 013 times s. Why? Now, why is that a plane? Well, let me draw some axes. Since the vector is three-dimensional, we have 3 dimensions, so this is x, y, and z. Now, 111 in my terrible writing, 111 would be 1 here, 1 here, 1 here. So you do kind of like this, and then up 1. So that's 111. Okay, and then 013, let's try a different color. So we'll do 013 would be 0 along x, 1 along y, 3 along z. So 1, 2, 3. So that would be this one here. Let's see, 013, so that's going to be like up here. Okay, so just kind of have to use your imagination. And I tried to draw this same kind of curve last time, that if you think of these two as arrows, then you kind of you find all lines that pass between the two. So the plane would be something like, if you imagine taking any line from any point on this one to any point on this one, all these lines, that forms a plane. I hope that you can develop that kind of geometrical intuition. All right, now I'm not going to draw this plane, but it's the same idea. Now there's a little bit different here. Here you have 030k and 204m. Now these k and m are arbitrary constants. This t and s are arbitrary constants. The letters don't matter. They're just variables. I could have used x, y, z, w. All right. Now, these are just arbitrary constants, and that reflects the fact that all of these points are on this plane determined by these two vectors. Now the difference here is that this is an offset. Okay, this plane here that I showed here actually goes through the origin, because if I take 0 times the first one plus 0 times the second one, that will give me the point 0, 0, 0. All right, but here in fact the point 0, 0, 0 is not on the plane because it passes through this point. And I'm not exactly sure what kind of direction it is, but it's going to be some kind of plane. I don't want to draw this because I've already stretched the limit of my artistic ability. But you can see that typically when you have two planes, I mean, you can do this with 2 pieces of paper, just hold it in space. Typically, you'll get an intersection that's a line. Sometimes if the 2 planes are parallel, you'll get no intersection. If the 2 planes are actually the same plane, you'll get the entire plane. But you would never get the intersection of 2 planes to be a point. So you expect the intersection is either a point, I mean not a point, it's either a line, it would be a plane, but the plane case is rare case. That's only if the 2 planes are identical, or nothing. All right, so how do we find the intersection? In fact, we did a similar problem last time. We want a point that's on this plane over here and also on this plane over here, so we just set them equal. Okay, and we'd get 1, 1, 1 times t plus 0, 1, 3 times S is equal to 1, 1, 0 plus 0, 3, 0 times K plus 2, 0, 4 times M. Okay. Now let me rearrange that. And we had this discussion yesterday about whether you want to put all of the terms on one side or leave the constant on the other side. Here you have 1, 2, 3, 4 terms that depend on variables, and then here you have a constant here also. So it seemed that people preferred to put the constant vector on the other side of the equal sign, which is fine. So if I rearrange this, I would write this as 1, 1, 1, T plus, I'm going to run out of space, aren't I? 0, 1, 3, S plus, or minus, well, I can do plus 0 minus 3, 0, because I'm bringing it to the other side, times K. That's a 0, sorry. Okay. And then plus minus 2, 0, minus 4 times S. And that's going to be equal to 1, 1, 0. Now, this is a system of 3 equations in 4 unknowns. So you can convert this to a matrix. And solve. And since I ran out of space, I don't know if I can insert a page. I don't know if it will let me do that. But since I ran out of space, let me stop here. I may do another example of this later on, but that's how you would solve this. The solution, the intersection of these two will be the solution of this system of equations. The system of 3 equations, 4 unknowns. All right. Now, if you remember how I did this last time, there would be a T column, S column, K column, S. T, how come there are 2 S's? Oh, that's M, sorry. Should probably do that. That's an M, not an S.
Dr. Thorne, you can add a page on the top center. See it says 4 out of 12?
I can, but I already have pages afterward.
Yeah, it'll insert between.
Oh, really? So I click here?
Yeah.
Okay.
And then go to...
Oh, you put here. I see. Yeah, okay. All right, very good. All right, thank you. All right. So let me... I don't know if I can see. That's the thing. I can't do copy paste. Can I? Or can I? If I do this select, it won't let me select. It won't let me lasso, or will it? I guess not. Well, that's okay. So let's see if I can remember this. You help me remember this. The first column is 1, 1, 1. Second column is 0, 1, 3. So let's go ahead and do that. So this is going to be 1. Whoops, it's not on pencil. 1, 1, 1, 0, 3. Okay, and the next one.
The other ones, we brought them all to the left?
So these all go in the same.
Okay.
Yeah, these all go in the same matrix, right? 0, minus 3, 0, and then
-2,
minus
0,
2,
-4.
0, -4. Okay, and then if we're going to do augmented, we draw our line, and on the other side was what? 1, 1, 0. So let me see what's the best way to do this. I wanted to avoid doing this, but you can see that this solution, since there are 4 unknowns and only 3 equations, this solution will have an arbitrary parameter. And you can find examples of this in the book. Okay. So the solution will have the form It will look like some vector, let me just say something like ABC, plus, and then you can write some parameter. You can make it T, you can make it anything else, and then this would be times DEF. So that's how you would write it. You would not, this would not have a single solution. It's going to have a family of solutions. Right? If you have trouble with that, we may come back to this, but I want to go through and at least cover the concepts of each type of problem that we're going to be looking at. So let me leave this here for now. If we have time, we'll go back and solve it explicitly.
Can I ask you a question?
Sure.
What, so the vertical line would represent an equal sign. So what,
yes.
In the solution that has this form with it, where you wrote ABC, like where does the equal sign go? Is there one?
You don't write it equals in a solution. Well, I mean, you can just say, because the solution is a set, right? So if you want to say this is a set where T is in R. This is the solution set. It's the set of solutions.
So this would be giving a set of points that all lie on the plane that...
Any point of this form is a solution, is on both planes. Okay. Just like this, right?
Yeah.
Here, this is giving me a plane, right? This here is giving me a plane. This here is giving me another plane. Okay. What I have here is a set that is the intersection of those two planes.
Does it matter, Dr. Thorne, does it matter if we use the T or an M?
No, it does not.
Okay.
It does not matter at all. Letters, don't get hung up by letters. If you have a variable, it can be anything. Sometimes it would be useful to, M would be fine. And if you solved it, you probably would use M because M is the last column. But any kind of variable is fine. If I go to his textbook, which didn't open yet, let me see if I can find it. Just let me open his textbook quickly. Here we are. And maybe we can see some examples. This one's kind of far on. Sorry?
May I ask a question?
Sure.
From the structure of the answer, how do you determine if the intersection is a line or a plane?
Okay, all right, very good. Now, it didn't ask what it was, but you can determine from the form because, again, think about this geometrically. What is this solution saying? Let me go back there. Why doesn't it ever show my browser? Okay, if I do have a solution like this, sorry, this is a plus and that's a T. I hope that's clear. This is a plus and that's a T. I try to make a curly thing on my T to distinguish. What this is saying is I have this point in the solution and then plus some arbitrary multiple of this vector. Now, how would that be represented geometrically? Well, I'd have the point ABC on my axes. So let me draw my axes over here. ABC would be some point here. And then my vector pointing from there would be DEF, right? That's my vector DEF. And any multiple of this vector is on the solution. So in fact, the solution is going to be, include this point and any multiple of this vector. So in fact, it's a line. So you see this picture is very similar to the picture I put here. Here I had two vectors and any linear combination of those two was a point on the plane. But if you just got one vector, there's no linear combination. You just scale that vector and you go back. I mean, you're only allowed to go along that direction. If you're only allowed to go in that direction, you can only go on a line.
Does that mean that if there were two free variables, then the solution would be a plane?
Exactly. Yes. I mean, if you had, yeah, it's
as long as there was a solution.
Yes, yes. So the solution is a set. Okay. Well, hopefully, I think it is, I'm glad you asked that question because it is important to have a geometrical idea of what's going on. This linear algebra is so much geometry. So you can, if you like making manipulatives or something, or taking pieces of paper, just take pieces of paper and do stuff with them. You have a coordinate system which is a corner of your room. That's your coordinate system. So you can, this is stuff you can visualize. Okay. All right, next one. Find the reduced echelon form of each matrix. Right. So I'm going to do an easy one. I'm going to do D. Reduced echelon means that each column with a 1 has no other non-zero entries. Okay. So maybe I can say that each leading entry in each row is a 1 with no other non-zero entries. In that column. Okay. So for example, if I have a 1 in my first row here, then these would all have to be zeros. Okay. Now it's possible I could have something like a 5 here. That's possible. Then maybe I'd have a 1 here. This has to have all zeros. And this is the leading entry, so that's also 0. And then I could have a 6, 2, and then I could have another 1. Okay, something like that. All right. So this here is row echelon form. This is a row echelon form. Okay. Typically, you're going to have a 1 in every column. So this one here, this one here, this one here are the leading entries in each row, and you can see the leading entry in each row has zeros for the other entries. All right. So that's what I want to do. So let's look at D. Okay. Now, if I take D, you can kind of see that the leading entries go down in this stair-step pattern. That's the other thing I neglected to mention, is that the leading entries always go, the leading entry of subsequent columns is always right to the leading entry of previous columns. So it looks like I'm going to want to rearrange this. I think what I want to do is I want to move row 3 up to row 1, and I want to move row 2 down to row 1 down to row 2. So I'm just going to say that I'll say rearrange rows, which you can do. I would actually have to do 2 different row exchanges. But if I rearrange the rows, you can see I can put the last row first, 1, 5, 1, 5. Then I can put this row second, 0, 1, 3, 2. Then the last row, 0, 0, 5, 6. Okay. All right, now, you see this is not quite in reduced row echelon form. This is in row echelon form, almost, if I change this to a 1, but it's not reduced row echelon form because there's no 0 here. So what I have to do is kind of go back and zero out the other entries in these columns. So in order to do that, I would take row 1 and subtract 5 times row 2. And that will zero out this 5 here. Okay. Now, before I did more than one, well, you can do more than one. In this case, I only want to do 1. So I'm going to, so again, I'm referring to the row 1 and row 2 in this matrix here. So row 1 minus 5 row 2 is 1 here. 5 minus 5 times 1 is 0. 1 minus 5 times 3 is minus 14. 5 minus 5 times 2 is minus 5. And the other ones will just leave the same. 0, 1, 3, 2. 0, 0, 5. Well, here, why don't I just go ahead and change the last row. I'll take R3 over 5. Okay. That way that's not going to conflict with the operations I did here. So that's going to be 0, 0, 1, and 6 over 5. Okay. All right, now all I have to do to make this row echelon is to get rid of these non-zero entries. Okay. So my next set of operations, well, to get rid of the minus 14, I'm going to have to take R1 plus 14 times R3. To get the next one, I'm going to have to take R2 minus 3 times R3. Okay. And if I do that, and I'm not going to do it because I think you should be able to do it, this is still going to be 1 and 0 here, because as you see, this R3 has no non-zero entries here. Then when I take R1 plus 14 R3, this 1 will multiply by 14 and give me a 0. And then there's going to be something here. I don't know what it is. Some S. Okay. All right, now how about the second row? If I take R2 minus 3R3, this is 0 minus 0, which is 0. This is 1 minus 0, which is 1. And then this is 3 minus 3, which is 0. And I'm going to get something else here. And then I have 0, 0, 1, and then something here. Or 6/5. That's going to be the same. Okay. So you can see this has the correct pattern. The leading one in each row has no other non-zero entries. And the nice thing about this is you can read off the solution directly. If this represented an equation in x, y, and z, and this was the augmented, this would be z equals 6/5, y equals whatever, and x equals whatever. So that's the usefulness of reduced row echelon. You don't have to do back substitution like I did last time. Does that make sense?
Yes.
All right, so you can go ahead and, I invite you to watch the video again, go back and rework the problems. You do have access to these here. All right, so decide if matrices are row equivalent. So I'll do an easy one. Let me do this one here. So you just need to remember what row equivalent means. Row equivalent just means they have the same row echelon form. Now, there's another way of defining it, but practically that's what it means. It means that they have the same reduced row echelon form. I didn't say reduced. You have to say reduced. Have the same reduced row echelon form. And here I'll say, okay, reduced row echelon form. Okay, so you just need to reduce both matrices. That's the easiest way to do it. So you just take, if I just take 1, 1, 1, give another little practice here, minus 1, 2, 2. All right, so what am I going to do here? Pretty clear that I want to get rid of I want to get a 0 here, so I'm going to do, so R1 will stay the same, and I'll take R2 plus R1. Okay. So that's 1, 1, 1, and then R2 plus R1, minus 1 plus 1, 0, 2 plus 1, 3, 2 plus 1 is 3. Okay. And then here I'm going to take, I'll take R2 divided by 3, and here I can also take R1 minus R2 over 3. And that's not a conflict because this one is based on R1 and this one's based on R2. Okay? So if I take R1 minus R2 over R3, remember this R2 refers to this R2 here and not to the R2 I'm making over here. So this is 1 minus 0, 1 minus 1, 1 minus 1, and then this will be 0, 1, 1. Okay? All right, so that's my first matrix. So let me call this A, and I'll call this B. So that's reducing A. Let's see if we can reduce B. B would reduce as 0, 3, minus 1, and then 2, 2, 5. The easiest way to deal with this first is just exchange them. So that would be 2, and so that's 2, 2, 5, and then 0, 3.
Exchange them and divide by 2 in one step?
Yeah, you could do that. You could do that. I just don't know how to show that. You could certainly do that. Yes, and I can divide this by 3. So let me just go ahead and do I can actually do a bunch of things here now. I can say, well, let me just do I'll just do it out longhand. So this is R1 over 2, and this would be R2 over 3. And so that would give me 1, 1, 5 halves. And this would give me 0, 1, minus 1/3. Okay. All right, so I'm almost there. I just need to take R1 plus R2. And that will give me, I think I can fit it here. So the 1 will stay the same, R1 plus R2, I'm sorry, R1 minus R2, sorry about that, R1 minus R2. R1 minus R2 gives me 0. 5 halves plus 1/3, well, let's see, that's going to be 15/6 plus so 17/6. And then here I have 0, 1, 0. Okay. Now, reduced row echelon form is unique. Well, it's not, yeah, reduced row echelon.
Why did the last number become 0?
Oh, because I screwed up. Okay.
Negative 1/3.
It's going to be minus 1/3. So the reduced row echelon forms are not equal. So they're not row equivalent. That's as easy as that. All right, by the way, I do mention on this exam, which is here, I have posted the quiz. You can see it here. It's called Screening Exam. So I really should do this weekend. If you do the exam and you're unsure about your result, please go ahead and contact me on the weekend. It's not a problem. If it seems like you don't feel ready or it's harder than you thought it was, go ahead and contact me because you want to get things sorted out before the semester starts. So this is the quiz, blah, 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 and I can go to, if I go to preview, it says, so you can say all 9 questions are on the PDF, which is here. If you wish, you can hand in your work here. See, you can upload it here, so I can make comments. I'm not going to grade it, but I may make some comments. I will post the answers. You should be able to do this with a basic arithmetic calculator and no programmable calculators to do your matrix calculations. That's something you should be able to do. Now, it's better if you can do the exam without references, but if you forget some things, you can consult the textbook or some other written reference. But try to do as much as possible without any reference. And I think I gave you 120 minutes. I believe that's how much I gave you. And there are 9 questions. So that's how that works out. And my clock is running. So let me go back. Okay. It says no time limit, so that's wrong. I'm going to put on a time. I don't know why there's no time limit. I thought I put on these stupid things. You do stuff and it doesn't save. So you have to go back and check it. So I think 120 minutes for 9 questions is more than enough. Okay, so let's go back to our sheet here. All right, so that's this one here. Let's go on to, we've got a bunch more stuff to do. Okay. All right, now, a lot of these questions are just understanding what it's asking for, and it all reduces down to the same type of calculation. All right, so here it says, decide if the vector lies in the span of the set. Okay, inside of the space. Okay. All right. Now, so here, so the vector. So let's do A. So for A, the vector. It's a little hard to see, but the vector is 2, 0, 1, and the span is the span of. He writes it this way: span of 1, 0, 0. And 0, 0, 1. Now, what does it mean for a vector to be in the span? And what we're getting here is just this span determines a plane. We saw how 2 vectors determine a plane. So this vector is in the span means that the vector is in the plane determined by these two vectors. Now in this case, it's two vectors in 3 space. In another case, it might be vectors in multiple vectors. But the idea is the same, that this vector here is in the geometrical set that's determined by these vectors. So in other words, this vector 2, 0, 1, now how do we algebraically specify this plane here? Well, it's some combination of this vector plus this vector. That's how we form plane in the first example I did today. So I can say x times 1, 0, 0 plus y times 0, 0, 1. Okay. Now you can go ahead and write this in a matrix form, but look at this for a second here. You have 2, 0, 1, and you want to see if it's in the span of 1, 0, 0, and 0, 0, 1. Now these are all zeros. So this first vector is not going to affect the two components here. The second vector has zeros up here. It's not going to affect the two components here. So in fact, in order to make this work, this had better be 2 to match up this 2, and this had better be 1 to match up this 1. So in fact, this has a solution. X equals 2, y equals 1. So in fact, 2, 0, 1 is in the plane. So yes, so the vector 2, 0, 1 is in the span. Okay. In this case, often when you have this type of problem, you can look at it and say, well, this is what it would have to be. Right? In fact, if I had 1, 1, 0, then it's quite clear that it would not be possible. Because in order to get the 2 to work, this would have to be 2, then I have a 2 sitting in the middle, and that wouldn't work. Okay? So often you can just look at the problem and see whether it's going to work or not. Okay, we can jump in with questions at any time. I'm just going to keep on moving if I don't hear anything. Go on to this one. Okay, now this is, yeah, go ahead.
Right, and the one that you were just working,
Yes.
B has all kinds of algebraic.
Yeah, don't worry about it. Don't worry about it. Don't worry about it. I don't. Yeah, no. I'll talk about that some other time. Right now, I just want to make sure that you know how to work with vectors in n-dimensional space, in particular R2 and R3.
Okay.
We'll talk about that later. All right. So and I tried to assign problems that only involve that type of vector. I just say parenthetically that one of the wonderful things about linear algebra is that all kinds of things are vectors that you wouldn't expect, including functions, polynomials, matrices, all kinds of stuff. So whatever you do in linear algebra also applies to a whole bunch of other things that you would never expect. In fact, calculus reduces to linear algebra. So I won't say any more about that. All right, so decide whether each subset of R3 is linearly dependent or linearly independent. Okay. All right, now what does it mean? So here, it's just a question of what does linearly dependent mean? Or linearly independent. Linearly dependent means that that there is a linear combination, and I have to say a non-trivial linear combination of the vectors that gives 0. All right, so let me see if I can give you an example. Suppose I do, like, let's look at B, for instance. You can see B has 1, 7, 7, 2, 7, 7, 3, 7, 7. Now, it's quite clear, well, actually, Yeah, well, let's try this. So I have 177. This is interesting. All right, well, let's try this. So 177277377. So the question is, if I take 177, 277, and 377, I'm going to write it this way. And I'm going to take some linear combination of these three. Linear combination means I take a arbitrary constant times this one, plus an arbitrary constant times this one, plus an arbitrary constant times this one. And I get that equal to 0. So notice that this is, well, I should say 0, 0, 0, sorry. Right, this is actually, this is a homogeneous equation, right? So basically, you form a homogeneous equation out of your vectors. If it has a solution, then they're linearly dependent. If it doesn't, then they're linearly independent. Okay, so let's try to solve this. So this would be 1, 2, 3, 0, 7, 7, 7, 0, and 7, 7, 7, 0. Now, it's pretty clear that I can take care of these 7s here, but I can take, for instance, I can take R2 over 7, and I can take R3 minus R2. And that's going to give me 1, 2, 3, sorry. 1, 2, 3, and 0, 1, 1, 1, and 0, and 0, 0, 0, and 0. Okay. And then, of course, I can take I can take R2 minus R1, and I get 1, 2, 3, 0, and then here I'm going to get R2 is going to be 0. Well, it wasn't the best choice. Minus 1, minus 2, and 0. And then 0, 0, 0, and then 0. All right, now, this does have a solution. I have an arbitrary parameter in the last place. Well, let me go ahead and solve that because that was kind of like the other one. And this is kind of an easy example. So what I had here is, so this is continued. So that I think I had 1, 2, 3, and 0. And I had 0, minus 1, minus 1. Minus 1, minus 2. 0, and then 0, 0, 0, 0. Okay. Now, there are a bunch of ways you can express this. I'll just go ahead and do back substitution. I can use the variables x, y, z. You could use KLM. It doesn't really matter. Okay. So this last equation is telling me minus y minus 2z equals 0. And that's the same thing as y is equal to negative 2z. And then the first equation gives me x.
Wouldn't that be positive? Oh, no. You did the no. I'm sorry. You're right. You're right.
Okay. So here I have x plus y plus z. I'm sorry, x plus 2y plus 3z equals 0. That says x, and then 2y is going to be minus 4z plus 3z equals 0. So that means that x equals z. All right, so what do I have here? Any solution, so any vector of the form z can be anything. Y is minus 2z. X is equal to z. All right? So I can write that as z times 1 minus 2, 1. So that's, I could have done the earlier problem like that. If you like to do things another way, that's fine. This is just one way to do it.
So, can we finish answering the question though? Because So this
Okay,
is,
what was the
if there are
question?
many solutions, is that still?
Okay. Let's see. Yes, it's linearly dependent because there's a solution.
So it doesn't have to be a unique solution. There just has to be at
Yes.
least one.
Yes, that's right. Yes, that's right. Yes. So,
And
okay.
also, can you, in the directions, when they say subset of R3,
Yes.
they're giving three vectors.
Yes.
I just maybe don't understand the wording of the question. I understand what we
Okay.
did in the process, but
Okay. Oh, all right. So in his notation, if you see these angle brackets here,
Mhm.
the way what this means is the span of these three vectors. Let's see. No, it's not. Sorry, it's not angle brackets. He said that this is the set of three vectors. So since it's a set and each element is in R3, this set of vectors is a subset of R3.
Okay.
Right. I mean, so
Basically,
each word makes sense, right? Decide whether each subset
Yeah.
of R3, this is a subset of R3. It's linearly dependent if I can find some linear combination that gives me 0. Right. Otherwise,
and
it's linearly
geometrically, what is it? What is the importance of this?
Well, geometrically, what it would mean is that, in this case, it would mean that, all right, so if you can get this solution, so what we found is that, for instance, let's see, so, sorry, I didn't leave myself room. In this case, one solution is 1 minus 2, 1. That's a solution, right?
Yeah.
So if I go back here, that means that 1 times this minus 2 times this plus 1 times this equals 0. Now, I could bring these two to the other side. That means that this vector is in the span of those two. And what does that mean geometrically? That means that this vector is in the plane determined by these two. So a simple way of saying that they're linearly dependent is all three of these vectors are in the same plane.
Okay, there, that's what I was looking for.
Yeah, all three are in the same plane. But if you get some linear combination of these three vectors is equal to 0, I can bring one to the other side, and that means that this one is a combination of those two. And we know what that means. That means that this is in the plane spanned by those two. So it does have a very geometrical interpretation. All right, so I did this. Okay. So represent the vector with respect to each of the two bases. All right, so what does it mean to represent a vector with respect to a basis? Okay, this is really just the same thing. What this is saying is express the vector as a linear combination of the vectors in the basis. Now this is really just the same problem using different words. It's really just the very same problem. So what I want, here's my V and here's my basis. So if I want to find express V in V1, that means I solve 3 minus 1 is equal to x times 1 minus 1 plus y times 1, 1. Now, if I wanted to do that, I just go ahead and do the row echelon form. Because these are my two variables, I have 1 minus 1, 1, 1, and then this would be 3 minus 1. And you solve that. So your solution gives the coefficients x and y. Okay. Now express V and V2, it's the same thing. In this case, you'd solve 3 minus 1. But in this case, you're going to write 3 minus 1 is equal to x times 1, 2, plus y times 1, 3. Okay. And that would be the same thing. In this case, you're solving a different matrix, right? 1, 2, 1, 3, and then 3 minus 1. So it all comes down, you can bet that almost every problem that we do is going to reduce to some kind of matrix problem, something like this. Okay, so all you would have to do to solve this problem is solve this system, and then the solution just gives you the coefficients. That gives me the expression.
Can I ask a question?
Sure.
I had trouble with this one for trying to understand the basis. So if those two vectors, B1 and B2, are bases, then they are a sequence of vectors that are linearly independent. So V would have to also be linearly independent as well if it's a basis?
No. In fact, since V can be expressed as a combination of these two, that means that these three vectors are linearly dependent. Because I could put this on the other side, and I would have x times this vector plus y times this vector plus minus 1 times this vector is equal to 0.
But it would be linearly independent.
What would be linearly independent?
3, negative 1, V, vector V.
Then you never have a single vector that's linearly independent. You only have a set that's linearly independent.
That's what I did. Okay, thank you. There's
no such thing as a vector that's linearly independent.
That's what was confusing. Thank you.
Okay. All right, so here it says find a basis for and the dimension of the solution set of the system. So just go ahead and solve it. Suppose we solve this system. Well, you can see this is a homogeneous system. If I was going to solve this, I would write it as a matrix. 1, 2, minus 4, minus 8, 3, 6, minus 1, minus 2, and I could put 0, 0 here. Okay. Now you can see there seems to be a kind of relationship between these two rows. In fact, if I take R2 minus 2R1, I end up with 1 minus 4, 3 minus 1, and then 0, 0, 0, 0. Right. Now, in fact, this is reduced row echelon form. This is reduced row echelon form. Why? Because there's only one leading non-zero entry, and there are zeros in that column. These are all non-leading entries, so they can be anything. So what this is saying, if I was going to, oh, sorry, I forgot the 0, 0, sorry. So what this is, if I make this x, y, z, oh, I see, he does x1, x2, x3, x4. So I can write this as x1 minus 4x2 plus 3x3 minus x4 is equal to 0. Or I could write this as, how would I write this? My x4 can be anything. My x3 can be anything. My x2 can be anything. It will work as long as I have x1 is equal to 4x2 minus 3x3 plus x4. As long as this holds, then I have a solution. So my solution is the following. I can have x4 can be anything. X3 can be anything. X2 can be anything. Well, let me give myself a little more room. X4 can be anything. X3 can be anything. X2 can be anything. X1 has to be 4x2 minus 3x3 plus x4. Right? Now I can write this as, so you see that I have three arbitrary constants. I have x2. Now, what terms have x2? Well, there's a 4 here, there's a 1 here, no x2 here, and no x2 here. I'm just pulling out the coefficients of each variable. Now here I have x3. There's a -3 here. There's a 0 here. No x3 in the second. There's a 1 here. There's a 0 here. And then I have plus x4 times, there's a 1 here, 0, 0, and 1. Okay. Okay. So this is a linear combination of 3. So this is my basis. That's my basis. Those 3 vectors.
But what's the difference between a solution and a basis? Like, why do we need 2 words?
Well, the solution is this set determined by this linear combination. The basis is the vectors that form the solution.
Okay.
Right.
So,
the basis.
So without x2, x3, x4.
Say again?
So the basis is those. Without the x2, x3, x4.
That's right. The basis is the set of vectors. So if I call this V1 and I call this V2 and I call this V3, the basis is this set V1, V2, V3.
He calls it a sequence. That kind of helped me understand it a little bit better. A sequence of vectors.
Okay. And since there are 3 vectors in the basis, it's 3-dimensional. The dimension is the number of vectors in the basis. So again, what you do here is all you're doing is solving this system, and then you have to interpret it. And the interpretation is the vectors that form the solution are the basis, and the number of vectors is the dimension.
And the number of vectors depends on how many free variables you have?
That's right, because each free variable is going to give me a different vector. You see how I pulled this out? How I pulled them out into separate vectors? So
and
that's
sometimes,
exactly right.
Sometimes there's a vector that isn't multiplied by anything, like when we had a line. So that one wouldn't, if it was in that form, it wouldn't count?
Well, in that case, you would not have, you wouldn't talk about basis.
Okay.
And now that only happens when you have a non-homogeneous system.
Right, because it would be...
because you'd have vectors, yeah. So when you have a basis, you only talk about basis when you have a homogeneous system.
So if it's offset, then you don't have a...
No, you don't say that's a basis then.
Okay.
And I won't go in for the reason for that, but there's a reason for that. So if you see a question asking for basis, you won't have to worry about that issue. Okay. All right. So here's matrix multiplication. Now, so just remember that if you have a matrix A times B, then if A is n times m, is n by m, and B is P by Q, you must have m equal to P. That's the necessary condition. Or in other words, if I write it this way, it may be more clear. If I have n rows and m columns, then this must have m rows, and I can call this q columns. It really doesn't matter. So the number of columns of the first is equal to the number of rows of the second. All right, so you can, in that case, you can kind of read things off. Here I have 2 columns, 2 rows, that's good. Here I have 3 columns, 3 rows, that's good. Here I have 2 columns, 3 rows, this is no good. But the others are all okay. All right, so let's look at this one. 5, 2, 3, 1, minus 1, minus 1, 2, 3, minus 5. Now, the result of this is going to have the number of rows of A and the number of columns of B. So this is going to be n by q. That's always true. The number of rows of the result is equal to the number of rows of the first matrix. The number of columns of the result is the number of columns of the second matrix. So how do you do this? Well, the first entry here, which I'll put in, oh, they only have a limited, okay, highlighter. Okay, good. All right, so I'll highlight this. All right, so this entry here. How to get this entry here? Well, this is the first row and the first column. First row and first column means I take the first row of this and the first column of that. And I do what's called the dot product. So it's going to be 5 times minus 1 plus, was that a 2? Yeah, 2 times 3. I think I can probably draw over it. So this entry here is going to be 5 times minus 1, then plus 2 times 3. All right, now that's one entry. That's a single entry. It's not two entries, that's a single entry. Now let me erase this so I have more room. In this case, if you have 2 by 2 by 2 by 2, the number of terms in each entry is going to be equal to the number of columns of the first one. All right, so that's the first entry. Now, if I wanted to get this entry, let me go back to highlighter. Highlighter's here, so I'll do green. All right, if I want this entry here, what about this entry? Well, it's the first row and the second column. That means I take the first row of the first matrix. The row is determined on the first matrix. The column is determined on the second matrix. So I'm going to take this, I'm going to take this row times this column. Let me erase that because that's just, okay. So that's going to be 5 times 2 plus 2 times minus 5. All right. All right, now let's do this lower entry here. And I think I have just enough highlighters to do this. This entry here. What's going on here? Well, it's the second row and the first column. Second row here, first column here. So I'm going to take this row times this column. And I'm going to erase that so you can see what I'm doing. So that's 3 times minus 1 plus 1 times 3. Okay. And then lastly, I have the entry out over here. I think I have one more highlighter. Well, it's blue or black, whatever. Well, I'll use the blue because it's a highlighter. Right? All right. So this is the second row, second column. So that means I'm going to take the second row here, second column here. Okay, so what does that give me? That gives me second row here is 3. Second column here is 2. And then here is going to be plus 1 times minus 5. And then just work out those 4 entries. All right, it looks like I'm going to have 1, 0, 0, 1. Okay. In fact, if you know anything about inverses, this matrix here is the inverse of this one, because what I ended up was 1, 0, 0, 1. That's what I ended up with. That's the identity matrix. All right, I think I've got one more page here. Oh, well, I don't have one more page. That's it. All right. So just to look back over what we did, we really did solve. All right. So, and like I said, you can access these notes from the syllabus page. Should go, if you go here, it will take you to a folder. Should be right here. And you'll have everything that I did. I also put the notes from the first lecture on the slides, so you have everything that I've done. This is what I just did. So I'll close this. All right, so if I just review quickly what I did, I didn't do that today. This was a reduced echelon. Remember what reduced echelon form looks like? Again, if you do forget what these terms mean, you can go back, look in the book. Or you can look at these notes if you want, that's fine. I don't mind if you look at these notes and refresh yourself what these things mean. But the important thing is that each leading entry in a row is a 1, and all the other entries in that column are 0. And they have a stair-step form. That's the first one. And then row equivalent just means I take the reduced row echelon form of the two matrices and see if they're the same. This one here, to see if a vector lies in the span, you just set up an inhomogeneous equation where the vector is the inhomogeneous part and the matrix is formed by the two vectors. This is an inhomogeneous equation. Next one here, to show whether it's linearly dependent, you set up a homogeneous equation. You take all of the vectors in the set and you create a homogeneous equation. If it has a solution, then they're linearly dependent. If it does not have, then it's linearly independent. Represent vector with respect to each. Now, see, this is exactly the same thing as that span thing. It's exactly the same. No difference at all. Very same problem. All right, but of course, you'll get a different answer if you have two different bases. If I find a basis, solve the system. The vectors that form the solution are your basis, and the number of vectors is the dimension. And this one here, multiplying matrices. I didn't add matrices, but I think that's. But if you add matrices, you just add them. You add the corresponding entries. All right, maybe I'll just do one quickly if I just want to take. So add matrices. 1, 2, 3, 4, plus 5, 6, 7, 8. That's just going to be equal to 1 plus 5 here because I'm adding corresponding entries here, 2 plus 6 here, 3 plus 7, and 4 plus 8. And if I was going to do the multiplication quickly, 1, 2, 3, 4 times 5, 6, 7, 8. Just do it. I mean, this should get to be the point where it's going to be automatic. It's 1 times 5 plus 2 times 7 right there. Next one is going to be 1 times 6 plus 2 times 8 here. This one here is going to be 3 times 5 plus 4 times 7. And then this one here is going to be 3 times 6 plus 4 times 8. Okay, I like to do this question because people often get hung up with this. If I do 1, 2, 3 times 4, 5, 6. Okay, what's the result there? First of all, what's the size?
1 by 1.
No.
Oh, then 3 by 3. Oh, that's the 3.
No.
3 by 1. 3 by 3 is the answer.
Yes, it's a 3 by 3. This is 3 by 1, and this is 1 by 3. Now, this is a 3 by 3 matrix. I mean, everybody gets tripped up on this. So this, in fact, because I do first column with all of these, so it's going to be 4, 5, 6. Second column is going to be 8, 10, 12. And last column is going to be 12, 15, 18.
But if you change the order, you'd get a 1 by 1.
Yes, that's right. So matrices do not commute. So gratifying having you in the class because you just fell right into the trap.
It's because I was rushing.
Okay. No, but you don't know how many people get that wrong.
I mean, I have the habit of writing it out, but given 2 seconds to respond from my head, I mess up.
Yes, but you don't know how many people just think, oh, okay, well, I mean, you got two vectors there, so you just take the dot product, but that's not how it works. Like you said, if I did exchange the order, it would be a 1 by 1. But, you know, if you want to keep from making a mistake, just write out the size, right? Rows times columns. These two should match. If they don't, it doesn't work. And the size is going to be the outer dimensions. Okay, well, so I think that we're at the place where, we're a little bit over, but that's fine. So I think we're at a good stopping point. Please, like I said, if you take the exam and you have any questions at all, contact me. Don't worry about it. It's a very important time. I don't want you to have any doubts. We want to kind of count the cost before we start the course. I said you should get a 70. I would say if you get a 60, you're probably okay, because I know it's been a while, but you should have at least some notion of these concepts. It shouldn't be like you're starting from zero. You should have some idea of what's going on. Otherwise, it's going to be tough to jump in, because we'll be moving fairly quickly. And I'll send out an email in the course Canvas about the first meeting, probably at 7:30 on Tuesday.
Did you say we're only using this textbook for the review part, and we're using something else for
No. For most of the class, we're using this textbook.
Okay.
But we will be doing the harder problems, because in fact it is an undergraduate textbook. So, but I guess what I think is that, you know, math, you do have to, it takes several times around to understand it. This time, it's more than exposure. This time, you need to understand what's happening, not just be able to go through the motions, but really understand what's happening. And that's why I've been emphasizing the geometrical aspect, because as I never get tired of saying, this is a very beautiful subject because you can approach it algebraically and geometrically. And it just ties a lot of things together. Okay, are we good? I will stop the recording, and